My name is Tom George. I'm the Director of Emerging Technologies at ViaLogy Corporation. At ViaLogy, I work on applications for advanced signal processing algorithms for a bunch of different applications, seismic, radar processing, imaging, and so on and so forth. Prior to joining ViaLogy, I was at NASA's Jet Propulsion Laboratory, where I was a manager of the micro and nanotechnology group. It was called the MEMS group. Basically, I created an interdisciplinary group. And we made a whole range of sensors for space and defense applications.
What recent progress has been made in the detection of explosives?
While people have learned a lot, the problem is extremely difficult. And the more we learn, the more we realize how difficult it is, especially when it comes to situations in Iraq and Afghanistan, where it's not so simple as being in a laboratory. In a laboratory, you could detect a gas relatively easily using existing techniques with laser absorption and so on and so forth. But in the field, there are a number of issues. You could have a bombed out region that has previous explosives and you're trying to detect fresh explosives, stockpiles there. You could have dust, you could have high temperatures from freezing to 120 degrees Fahrenheit. So a whole number of environmental factors can affect your detection. So it becomes an extremely challenging problem. And there's no one solution that works well. So it's kind of like the story of the blind man and the elephant. So each blind man just holds one part of the elephant and thinks that the elephant is the trunk or the leg or the tail or so on. When you put them all together, then you get the elephant. And so in our business, it's called having orthogonal sensing, meaning one sensor sees something that the other sensor is blind to. And so by combining orthogonal sensor inputs, you can try to get a picture of what the event is. Because one of the things that the warfighters really face in the field is false positives and false negatives. So you don't want to unnecessarily alarm people if there's nothing there. Or in the worst cases, when you miss an event, and that could be potentially catastrophic.
Which of the orthogonal sensors use lasers directly or indirectly?
Lasers have been used for many different kinds of applications. Lasers are used for absorption measurements, where you directly absorb the energy that's present in the light. Or lasers can be used for exciting fluorescence, which is a different form of measurement. Lasers can be used to ionize gases, and so the ionized gas can be fed into a mass spectrometer. It's a more gentler way of doing it rather than having an electron beam hit the gas molecules and ionizing it. And it preserves the explosive molecule. For instance, if you hit it with a high energy electron beam, you could break up the molecule, and all you'll have left are the fragments. And from the fragments, you have to kind of piece together that this explosive existed, whereas you can gently ionize it and get a more direct measurement, if you will. So a number of ways.
What's the definition of standoff detection?
Yeah, that's a big controversy, standoff detection, because people who measure substances from distances of millimeters to centimeters have thought that techniques are standoff techniques. Whereas I think the more the definition that people are kind of congregating around is several meters to several tens of meters. So you would think of, again, this would be an optical regime where you would have a laser then being able to traverse those distances and getting back signal from the target.
Are there any particular challenges the industry is facing?
We need more engineering talent. So I would like more, the younger engineers and scientists to join the field. But basically, we have to take a system view. So it's no longer important to just consider just the one measurement technique. Just going back to that blind man and the elephant, you have to combine them together, but you have to combine them in an intelligent way so that you know how to fuse the data and exactly find what the target looks like in multidimensional space. And so it involves computer scientists, algorithm developers, sensor makers, everyone coming together holistically, as they say, for a system.
What are some of the applications of nanodevices?
The obvious advantages of nanodevices is that they're very small. So you have savings in mass, power consumption, and size, which can be of great benefit when you want to make portable systems, either for land, terrestrial use or especially for space use. So nano comes in handy there. But nano is still immature in terms of the technology, the proof of the technology. And so there's still a lot of work to be done. It has a lot of promise. And that's exactly what my conference is focused on, which is to transition new concepts that are emerging from the laboratory in micro and nano all the way to systems level that can be deployed in the field.
What kind of sensors are used to detect things underground?
Current application is seismic sensing. And so we do, in fact, I just came off of a seismic prospect in Texas where we are doing three-dimensional high-resolution seismic surveys. Most of the large reservoirs in the United States have been discovered, and so now the game has shifted to a different niche where you have independent oil companies who have smaller prospects, and they're looking for much smaller reservoirs, in a way a needle in a haystack problem, but at 5,000 feet or even greater distances. And so what you need is higher spatial resolution and being able to locate porosity in the rock, and to be able to size those reservoirs correctly. So we use a combination of sensing as well as signal processing with advanced signal processing.